In the last chapter of locational marginal pricing, we will briefly discuss hedging. Topics include volatility of energy prices, forward markets, contracts for differences, relationship to capital formation, transmission prices, financial transmission rights, also known as congestion revenue rights, and revenue adequacy. First, volatility of energy prices. LMPs vary over time as supply and demand conditions vary. We saw with various examples, even with the offers staying the same, that as demand varied, prices varied. When prices vary a lot, they are said to be volatile. Let's consider a generator and a demand that are co-located at the same bus. Or more precisely, let's consider a generator and a demand that are exposed to the same prices, the same LMPs. These LMPs might vary over time. And each of these market participants, the generator and the demand, might actually prefer to be exposed to a less varying price over time. That is to say, they might want to hedge, which means to remove their exposure to the LMP volatility. In the previous discussion of offer-based markets, we did not discuss in details the difference between forward markets and real-time markets, except briefly in a couple of sections. We saw that real-time markets match physical supply and physical demand over short time intervals, shorter than day-ahead markets, and moreover, that the price outcome on any given day will depend on the supply and demand conditions on and throughout that day. The prices will tend to fluctuate considerably or be highly volatile. The day-ahead market provides a mechanism to reduce exposure to this volatility, and other forward markets provide a way for a generator and a demand or a representative of a demand, a load-serving entity or retailer, to agree to a price for a specific quantity of energy in advance of the day-ahead market. In the context of an offer-based economic dispatch market, such as our day-ahead and real-time markets, the most natural forward contract is called a contract for differences. This is a forward financial commitment. Other types of forward agreement are possible, but in this brief introduction, we'll talk about just contracts for differences. So let's suppose we have a generator and a demand, both exposed to the same LMP. A contract for differences removes both their exposures to variation in that LMP for a given contract quantity over a given contract period. The reason why this works is that generators might prefer higher prices, demand might prefer low prices, and generators would prefer to not be exposed to low prices, and demand would prefer to not be exposed to high prices. So generation and demand can hedge each other's exposure to unfavorable conditions away. And in particular, a contract for differences is an agreement between a generator and a demand that entails a payment by the demand to the generator equal to a contract quantity times the difference, that's why it's called a contract for differences, between a contract price minus the LMP. And this will apply for each pricing interval in the contract period. If the number turns out to be negative, that really means that the generator would refund money to the demand. The contract quantity is in megawatts. The contract price is in dollars per megawatt hour so that we can subtract an LMP from it. Since the demand will also be required to pay the ISO for its energy based on the LMP, then if it consumes a power level equal to the contract quantity in each pricing interval, its total payment would be the payment under the contract for differences, which is the contract quantity times the difference between the contract price minus the LMP, plus the money that it pays to the ISO, which is the contract quantity times the LMP. Notice that the contract quantity times LMP terms cancel out, leaving contract quantity times contract price. Similarly, the net payment to the generator will be the contract quantity times the contract price. If the demand consumes more than the contract quantity, or it consumes less than the contract quantity, then it will pay for, or in the other case, effectively be refunded for the deviation at the locational marginal price. This is very similar to the case of deviation of real-time quantity from day-ahead quantity. On the other hand, if a generator produces more than the contract quantity, then it will be paid more. And if it produces less, it will effectively pay back the deviation at the LMP. Again, as in the deviation of real-time quantity from day-ahead quantity. The implication of this, we won't prove it formally, but the implication is that the previous results about incentives will still apply even in the presence of forward contracts. In particular, if we look at the first order conditions for profit maximization of consumption and profit maximization of production decisions, they'll be based on the LMPs, not the contract price. So market participants will effectively behave just as we have previously analyzed in the absence of forward contracts. That observation needs to be tempered in the context of market power, of course. This fits into a larger picture in the context of capital formation. In particular, bilateral contracts, and a contract for difference is a so-called bilateral contract, a contract between two parties. Bilateral contracts between generators and demand have a very important role in the financing of new generation. Here's the reason. If a developer builds a generator and does not have a bilateral contract, then it is taking the risk that the LMPs are high enough to cover its capital and operating costs. With a bilateral contract, however, the generator can lock in a contract price, and by negotiating with someone who's willing to pay an appropriate contract price, the developer can assure a less volatile revenue stream that covers their capital and operating costs. That contract then furthermore allows for easier financing of construction finance compared to speculative development. It's easier to take a bilateral contract to a banker and ask for a loan than it is to turn up without a bilateral contract. Of course, there are a lot of details here. The counterparty, the demand, needs to be trustworthy, and so on. Now I want to turn to transmission prices. So far, we talked about the situation where a generator and demand were co-located, or more specifically, they were exposed to the same LMP. But if they're not co-located, they are effectively exposed to the difference in LMPs between their buses. Although they could hedge exposure to either the generator LMP or the demand LMP using a contract for differences, they will be exposed to the variation in price difference between those two LMPs. A financial transmission right, or a congestion revenue right, abbreviated FTR and CRR respectively, is a way forward to deal with hedging against this volatility or the variability of LMP differences. A CRR provides the right to receive the product of a contract quantity, again in megawatts, times the difference in LMPs between a notional point of withdrawal, that would be where the demand is, minus the LMP at a point of injection, notionally where the generator is. And that applies, as similarly to the contract for differences, to each pricing interval in the contract period. The CRR hedges the exposure of someone who acquires it against volatile LMP differences. In particular, if a generator and a demand have signed a contract for differences and they also possess a CRR, then the net payment by the demand to the generator can be made equal to the contract quantity times the contract price, as in the case of a generator and demand being exposed to the same LMP. Since prices are typically higher at demand than generation, CRRs will typically pay out positive amounts of money, at least in expectation. If I acquire it now and I'm looking forward to receiving payouts over the future, I can really only calculate the expected value of that payout. So the expected payout of over a contract duration will be positive. So there are various ways in which one might imagine that someone acquires a CRR, but if one is purchasing it, then since it has positive value, it can be expected that a typical CRR will cost money to acquire. A speculator might offer to sell a CRR based on the expected payout over the contract duration, plus, for example, a risk premium for taking on the risk that there may be some unanticipated high or low prices in the payout. But apart from a speculator offering to effectively create a CRR, is there any other source of money to fund the CRRs that doesn't involve speculation? Well, the answer is yes. And to illustrate that, we need to remember the notion of the congestion rent. Remember, the congestion rent was the difference between what the demand paid minus what the generators were paid by the ISO. And that difference, the congestion rent, accrues to the ISO. Well, in fact, it can be used to fund, that revenue stream can be used to fund CRRs, and it can be done in a way such that the CRRs do not involve the ISO taking a speculative position. The ISO can sell those CRRs, although in some cases they are given away or allocated. The question, though, is how much CRRs can be sold. So let's suppose that the ISO has sold or otherwise allocated to market participants a collection of CRRs. And we'll model each CRR, since it involves notionally an injection and a withdrawal, we'll model each injection as a generation, and each withdrawal as a demand. And the power level of the generation and the power level of the corresponding demand will be equal to the CRR contract quantity. Let's collect together the generation at all of the buses and the demand at all of the buses, and I'll write P primed and D primed for the corresponding generation and demand. This is called the implied dispatch. It's the dispatch that would be implied by the CRR injections and withdrawals. By 9.7 in corollary 9.3, if P primed and D primed are feasible for the transmission system, so that we could say that the implied dispatch due to all CRRs considered together simultaneously, that implied dispatch is simultaneously feasible, then what we would have from corollary 9.3 is that if lambda star is the LMP corresponding to an actual dispatch P star and a demand condition D overline, we would have that lambda star transpose times D prime minus P primed is less than or equal to lambda star transpose D prime D overline minus P star. The term on the left is what is owed to make good on the sold CRRs. The term on the right is the congestion rent. So the result we've just shown is that the revenue to the ISO from the congestion rent is adequate. We say that it's revenue adequate to fund the CRRs. This will be true so long as the implied dispatch is simultaneously feasible. So this tells us a quite straightforward rule in our issuing or selling of CRRs to market participants. In particular, the ISO only needs to make sure that the implied dispatch of the CRRs is simultaneously feasible. CRRs are typically issued for extended periods such as a month or longer and apply for all of the pricing intervals in that month. Sometimes they apply for a part of a month, such as the on-peak pricing intervals in the month. When the CRRs are issued, a so-called test system is used for testing that the CRRs are simultaneously feasible. If the test system used in the actual market, however, has smaller line capacities, or more subtly, if there is a constraint represented in the market that was not represented in the test system, then the revenue adequacy result no longer applies. There can be a revenue shortfall. And generally speaking, in such a circumstance, we need a derating policy. In other words, a mechanism or an agreement whereby the shortfall in revenue from the congestion rent covers as much of the CRRs as is possible, but the CRRs that cannot be covered because of the derating are effectively reneged. So in this short chapter, to summarize, we considered volatility of energy prices and transmission prices, and we considered how to hedge them. We defined financial transmission rights and congestion revenue rights, and we considered conditions for revenue adequacy. This completes all of the chapters in this course.